A robot builds your car. A robot delivers your package. A robot explores Mars 140 million miles away, and nobody's driving it. But then, your Roomba gets stuck under the couch for the third time this week. Is that a robot too? The answer is yes, and understanding why is going to completely change how you see the world around you. Welcome to Robotics 101, the complete beginner's guide. I'm going to take you from zero to genuinely understanding one of the most important technologies ever built by human hands. Let's start at the very beginning. Here's something they don't tell you in school. Scientists, engineers, and roboticists have been arguing about the definition of a robot for over 80 years, and they still haven't fully agreed. So let's break it down. The word robot was first used in 1920 in a Czech play called RUR, Rossum's Universal Robots, by a playwright named Karel Čapek. In the play, artificial creatures do all the labor humans don't want to do. The word comes from the Czech word robota, meaning forced labor or drudgery. That's a little dark, but also kind of accurate. For most of the 20th century, robots lived in two places: science fiction and factory floors. In movies, they were either terrifying killers or loyal servants. In real life, they were giant mechanical arms bolted to floors, doing the same welding motion 10,000 times a day. Neither image captures what a robot actually is. So here's a working definition, one that most roboticists actually agree on. A robot is a machine that senses its environment, processes that information, and takes physical action in the world with some degree of autonomy. That's it. 4 pieces. 1. It senses. 2. It processes. 3. It acts physically. 4. It does this with some level of independence. Let's unpack each one. Pillar 1. Sensing. Every robot needs some way to perceive the world. This could be a simple light sensor, like a robot that follows a black line on the floor, or it could be dozens of cameras, microphones, and radar sensors all working together, like a self-driving car. Without sensing, a robot is just a machine running a script. It can't respond to the world. It just does the same thing forever, regardless of what's happening around it. Think of sensors as the robot's nervous system. They're the link between the outside world and the robot's brain. Pillar 2. Processing. Once a robot senses something, it needs to figure out what to do about it. This is where computation comes in. At the simple end, a thermostat detects temperature, and if it's too cold, it turns on the heat. Very basic processing. At the complex end, a self-driving car processes camera feeds, LiDAR data, GPS signals, and maps all in real time to decide whether to brake, accelerate, or steer. The brain of a robot can be a tiny microcontroller that costs $2, or it can be a powerful onboard computer running deep learning models. The sophistication of the brain determines what the robot can actually do. Pillar 3. Physical action. This is what separates robots from pure software. A robot doesn't just think, it does something in the physical world. It moves, it grabs, it welds, it flies, it walks, it rolls. This physical component, called an actuator, is what makes robots tangible. An AI that recommends movies isn't a robot, but an AI that controls a robotic arm to pick and pack boxes, that's a robot. The physical action requirement is crucial. It's why a chatbot is not a robot. It's why a spreadsheet is not a robot. A robot has to reach out and touch the world. Pillar 4. Autonomy. This is the tricky one, and honestly, it's a spectrum. At one end, a remote-controlled car. A human is making every single decision. No autonomy. Most people wouldn't call this a robot. At the other end, the Mars rover Perseverance. It's 140 million miles away. Radio signals take 20 minutes to arrive. NASA can't drive it in real time. The rover makes thousands of decisions on its own every day. Where to drive, when to stop, how to react to unexpected terrain. In between, a factory robot arm. A human programmed it, but it executes the program without human input during operation. Moderate autonomy. The more autonomy a machine has, the more we tend to call it a robot, and the more complex and fascinating it gets. Let's go back to the Roomba. Does it sense? Yes, it has bump sensors, cliff sensors, so it doesn't fall downstairs, and often cameras or LiDAR to map the room. Does it process? Yes, it runs navigation algorithms to figure out where it's been and where it still needs to clean. Does it take physical action? Obviously, it's literally vacuuming your floor. Does it have autonomy? Yes, you press one button and it figures out the rest on its own. So yes, your Roomba is absolutely, genuinely, legitimately a robot. It's not as glamorous as a Boston Dynamics humanoid doing parkour, but it meets every criteria. You might be thinking, okay, interesting, but why does knowing the definition of a robot matter to me? Here's why. Right now, in 2025 and beyond, robots are quietly restructuring every major industry on Earth. Amazon uses over 750,000 robots in its fulfillment centers. They don't replace every human, but they change what humans do and how many are needed. In hospitals, robotic surgical systems like the Da Vinci allow surgeons to perform operations through incisions smaller than a dime, with precision no human hand can match unaided. In agriculture, autonomous robots inspect crops, detect disease, and apply pesticides with surgical precision, using up to 90% less chemical than traditional methods. In disaster zones, inside collapsed buildings, inside nuclear facilities, robots go where humans simply cannot. This isn't science fiction. This is Tuesday. And here's the thing. Every robot doing these jobs, every single one, runs on the same 4 pillars we just discussed. They sense, process, act, and do it with varying degrees of autonomy. Once you understand those 4 pillars, you understand the skeleton of every robot ever built.